Welcome back. Today we're going to close out our discussion on Green's functions. This was supposed to be a brief detour before getting back to Chebyshev polynomials, so I'm going to try to finish off everything we need to know about them. That's the theme of today. So, if you will remember, we said there were some properties for a Green's function with a pole at infinity. That is to say, the first was it is harmonic on omega without infinity, and bounded outside neighborhoods of infinity. And I think I gave a bad explanation of what that means last time, so let me focus on this and make sure I've stated this clearly. That if we were on the Riemannian sphere, that infinity is represented as the North Pole. So a neighborhood of infinity would be something like this. That is to say, it would be the set of all z where norm z is strictly greater than some number n, or r, or whatever. So what we are saying is that omega might be some set that starts down here and goes all the way up to infinity. It might go to infinity. The Green's function might diverge, might have a pole at infinity, but if we take out some neighborhood around infinity, then it's bounded on the rest of it. So that's the first criterion. Second, was that the Green's function turns into log of absolute value of z with perhaps some sort of remainder, some difference that's bounded as z goes to infinity. And the third was that g omega of z infinity converges to 0 as z approaches zeta for quasi every zeta in the boundary of omega. So those are three criteria, and what we're going to show first is that Green's function is unique. By that I mean that if we can find a function that satisfies these three criteria, then it is the Green's function. There are not two different functions that both satisfy this. So, to do that, we will start by saying let g tilde of z be such a function. So g tilde is some function that meets those three criteria. And we already have g omega z infinity. We've already defined it. We've given a formula for it. It was the energy minus the potential at a point. So let's construct a new function. H is g tilde z minus g omega of z comma infinity. Well, what do we know about H? Well, if we again think about the Riemannian sphere, and we think of omega as maybe here's the not omega, and it might have some holes in it. But omega we defined as the unbounded component. So if you'll remember, the whole concept here was that E is some compact set, and maybe it has holes in it, and maybe not. But the outer boundary of it, we go all the way up to infinity. So if we cut out some neighborhood here, say the red part can again be the places where z is greater than n for some n, some positive integer, really any positive real number, but well then, outside that neighborhood, let's call it, I don't know, d, on part of omega not including d, g tilde and g omega are both bounded. So h is also bounded outside that neighborhood. There's an upper bound for the first function, upper bound for the second function, lower for the first, lower for the second, so the difference between them will have to have some upper bound. What about on D? Well, if we take the limit here as z goes to infinity of h, that converges to log z plus difference of 1, O of 1, big O1, minus log z, big O of 1. That is to say, they both are dominated by the log part. Since we're subtracting, it will cancel out, and it'll give us big O of 1. The O of 1s are not necessarily the same number, but they are a constant. So, h bounded on D. The logs cancel out, and so somewhere near infinity, this converges to a constant, so it's bound on that as well. Therefore, h is bounded on omega. So I used part 1 about saying that it's bounded outside neighborhoods of infinity, and part 2 says that it's bounded in neighborhoods of infinity. So it's bounded everywhere on omega. Now, what we're eventually trying to get to is to say that h is constant. We're not there yet. Let's say if, excuse me, let me clear this. If h is constant, then we know that limit as z approaches zeta of h of z will have to equal 0 for quasi every zeta in the boundary of omega. And then we would just say that h is identically 0. We can find there are points where it's 0 and it's constant, therefore it's 0 everywhere. And if the difference between two functions is 0, then they are in fact the same function. So that's what we're trying to get to. So all that's left is to show that h is constant. And this took me a little while, and I had to look up some ideas. The idea being that if this is E down here with holes in it, doesn't have to have holes in it, but it could, but omega does not have holes in it. Omega is everything out here. Then the boundary of omega is also the boundary of E, the outer boundary of E. So I've been switching between these. Del infinity of E equals del omega. They're the same thing. There is a principle in complex analysis which says that on an open domain, which omega is, open domain is redundant, open and connected, that it cannot have an internal maximum. So if it has a max, or a min for that matter, those must be on the boundary. Now, if this were 0 on the entire boundary, if this were a regular set, then it would be 0 all along there. It's not necessarily regular, but it is 0 at quasi every point. And so what I was trying to figure out is, can we ignore those quasi every points? And there is a way to do that, which SAF gives, which is a generalized minimum principle. So the standard version would require it what I was getting at, sorry, I didn't explain this quite well enough, is that if this is E, it says it's 0 on almost every point, or quasi every point. If it was 0 on literally every point on the boundary, we would say, well, the minimum and the maximum would both have to be on the boundary, and the boundary is 0 everywhere, so the min and max are both 0, therefore the function is 0. But there might be exceptional points, and I don't want to try to draw what those look like. Well, maybe later. But there's a generalized minimum principle which says, let D be a domain in C bar. That was the other thing that hung me up, was that what if we are including infinity? Does that change the rules? With capacity of the boundary being positive. And we've said our probability measures are 1, so they're supported on the boundary, so it must be positive. And G is super harmonic. Now, I know we haven't really talked about super harmonic, but we said it was that the value at some point is equal to the integral of some such along the outer boundary of a circle. That's harmonic. Superharmonic is just saying to a greater than or equal. There's a lot of theory about that, but harmonic functions are superharmonic, because if it's equal, then it's greater than or equal. So the point is, we will still be able to use this property for harmonic functions as well as superharmonic functions. And bounded from below on D. And the limit z goes to zeta of G is greater than or equal to some m. For every zeta in the boundary. Or quasi every. Then G of Z is strictly greater than m for every Z in D unless G is constant. Let me double check this. I want to make sure whether it says every or quasi every. It'll work either way in this case, but I want to just make sure. Yeah, that's supposed to be a quasi every, not an every, I figured. Okay. Yeah, actually it probably wouldn't work if it were every. That's the whole point of this, is to allow us to have these few exceptions on a capacity 0 set. That's probably also why we insist capacity be positive up above, because if it were 0, then a 0 capacity set inside another 0 capacity set wouldn't necessarily be negligible. But this will do the work for us here. We'll just do a little find and replace here. D will become omega. G will become H. And now that we have this, I think this gives us everything. Omega. We already know it's bounded on omega. It's fully bounded, so therefore it's also bounded from below. So this H fits all the criteria. So therefore, and the value it's greater than or equal to is 0. We know it's 0 on quasi every point. So therefore we can say H is greater than or equal to 0 on omega. But here's the clever part. We could also use negative H. Negative H would meet the same criteria. It would also be harmonic, and therefore superharmonic. It would also be bounded below on omega, different bound, but it would still be a bound. And it would also be greater than or equal to 0 at quasi every point of the boundary, because it's equal to 0 on every point boundary. So therefore, negative H is also greater than or equal to 0 on omega. And well, there's really only one way that could happen. That something can be both greater than or equal to 0, and its negative also be greater than or equal to 0, and that's that if it is 0. So therefore, we get H is equal to 0. Or, well, I guess this is sort of actually the way it's written. I should be a little more careful. Same ideas, probably could be rephrased in a way, but it would say that H and negative H are both greater than 0, which is impossible, so therefore it must be constant. I guess that's really where we wanted to go with this. Okay, so to reiterate that then, we've got our function H, which is greater than or equal to 0, quasi every point on the boundary. Therefore, it's greater than 0, strictly greater than 0 on the set. But negative H would also have to be strictly greater than 0 on the set, which is impossible. Therefore, this statement here, g of z is greater than 0, is false, h of z. So h is itself a constant. I feel like I may have overcomplicated that. I'm not quite sure if there's any way to simplify it. The basic idea being that our function h was greater than or equal to 0 on the boundary of omega, and therefore h is strictly greater than 0 on omega itself. But this is also true. And since this is impossible, the theorem gives us an out, which says if these statements here about it being greater than 0 or less than 0, if either one of them is false, then the answer is it must be constant, and therefore it's going to equal 0. Okay, so what that ultimately concluded then was that G, arbitrary G that meets those three criteria, has got to be equal to G omega Z infinity on omega. So the Green's function is unique. So that's going to help us a lot because we have a form for the Green's function. So if we have some other function that we work with and it turns out to meet all those criteria, we can then replace it with the formula we already know for the Green's function. So we're going to use this right away. We'll give a theorem. If omega is simply connected about infinity, then G omega of Z, I'm switching notations again, same as the little g omega of Z infinity, is equal to the log of the absolute value of phi of z for z and omega, where w equals phi of z is the unique Riemann mapping from omega to the set of w where absolute value of w greater than 1. That is, say, the outside of the unit disk, and where the phi of infinity is infinity, phi prime of infinity greater than 0. So screenshot that if you need to. I need more space, so I'm going to move on to something else. So, to illustrate what we're talking about, let's draw some pictures here. So here's an E with two little holes in it. Omega is out here, simply connected. So there is a theorem, a Riemann mapping theorem, which says that we can take this to the unit circle. And the outside here will still be outside, and the inside will still be inside. That means those holes in E will be preserved. Maybe they'll change shape, get stretched or something, but there'll still be two holes in it. But the outer part has no holes in it, so it just fills in outside the unit circle. As opposed to, say, if we did something like this, where this, all the shaded black part, is E. In this case, omega, the outside, is not simply connected because it does have a hole in it. So it wouldn't work for that kind of problem. So we're going to focus on the ones where the exterior is simply connected. And we're going to say there is some mapping, a Riemann mapping. That means it is conformal, it is holomorphic and invertible with a holomorphic inverse. And we can use that to construct a Green's function. So let's see why this is. Okay. Well, if we have that mapping, phi of z, and we know that phi of infinity is infinity, and is there a parenthesis there? I don't know. Phi prime of infinity is positive. This actually tells us a lot about the form of phi, because phi infinity is kind of an isolated singularity, and so that means, and this is technically a limiting thing, or whether we treat infinity as a number or as a limit, it's kind of flexible. But we can create a Laurent expansion, that is, say, the same as a Taylor expansion, but allowed to have negative terms as well as positive. And it will have to have this form: z over c plus a naught plus a1 over z plus dot dot dot. So it might have lots of negative power terms, but it's going to have exactly one positive power term, and that's a linear term. Why is that? Well, phi of infinity equals infinity means at least one positive power. If we didn't have that positive power, then as we go to infinity, everything would zero out except for a naught. But we want to go infinity, so we need some power of z to be positive. But what about the derivative? Well, let's suppose, just for our contradiction's sake, we had z to the n and then, let me say this again. Let's just say we had a z squared. az squared plus a1z plus a naught plus dot dot dot. You could factor out the z from that, or z squared from that, even. Excuse me, let me double check, make sure I'm saying this right. I don't want to confuse anyone. Well, yeah, the idea was we could then factor out z squared. It would be a2 plus a1 over z plus a2 over z squared plus dot dot dot. And then if we took a derivative, we would get 2z times all this stuff plus z squared times all this stuff which again, if we plug in infinity, would give us infinity. But on the other hand, if we took the derivative of this function here, then we would have a 1 over c. So essentially what I'm saying is, since the derivative of infinity needs to be positive, we need for it to have no more than one z power term. Because if it had any higher power, the derivative would still have a z in it. I guess the factoring was kind of unnecessary. I could just say the derivative of this would be 2a2z plus a1z plus dot dot dot, and then this piece would go to infinity at infinity. So, our point then is that this is the form that the expansion of phi will take. So we had some weird set E will get mapped to a nice clean circle with radius 1 by this function phi. And C will have to be greater than 0 because it said the derivative is greater than 0. Phi prime is going to be, and infinity is going to just be 1 over c. So since we were told derivative has to be positive, then c must also be positive. Now, what do we know about this function here? And better yet, what do we know about this log function? Well, this function is harmonic when phi of z is non-zero. And since we said phi maps omega to the exterior of the unit disk, that is, the closed disk complement, everything outside the closed disk, so phi of z will have to be greater than 1. So we don't need to worry that this will be 0. So that's to say log of phi z harmonic on omega. What else do we know about this guy? Well, if we did log of phi of z minus log of z, that would give us, using basic log rules, so it would become log of 1 over c plus a naught over z plus a1 over z squared plus dot dot dot. And then if we take it to infinity, it will give us log of 1 over c. So this has already fit the first two criteria of the Green's function. As for the third, what happens at the boundary of omega? Well, if we remember, the way this worked was that phi mapped the boundary of omega onto the boundary of the disk of 0, 1. So phi of z has to equal 1 on the boundary of omega, which means log of absolute value of phi of z, or this should be absolute value, excuse me, has got to equal 0 on the boundary. Well, that's the third criteria of a Green's function. It's even a little stronger because it's every point, not just quasi-every. So therefore, log of phi of z is the Green's function. So that tells us something. This is good. We can find the Green's function if we have that sort of mapping that always exists, that takes some domain to the unit disk or the exterior of the unit disk. And that is a property of being simply connected, and that gets much deeper into complexness than I want to go, so I'll just say, trust me that as long as it's simply connected, we can find this. It's sort of a topological concept of stretching and squishing. We've got E in here. It's possible to distort this, to stretch it into a circle without having to tear any new holes in it. If there's already a hole in it or two, there will be holes in it at the end. But we can make this into a circle with the same number of holes. And since the exterior had no holes, the new exterior will have no holes. So that's good, because we know some other things about the Green's function already. We have a not a closed form, but we have a form of the Green's function which is that we know if we have VE minus U mu of E Z, that's the Green's function. So that means if we subtract log absolute value of z, we have shown this converges as z to infinity to just VE. The potential and the log go away. They approximately are the same thing, the potential and the log, and we're left with just VE. So, but we also just showed, just a moment ago, that the log of phi of z converge to 1 over c. But log phi over z is the Green's function. So, so when we put it all together, sorry, what was it we said? I'm sorry, I messed that up. I meant to say not log phi of z itself, but log phi of z minus log z goes to 1 over c. That's what we showed a few minutes ago. So therefore, VE equals log 1 over c. We work that out. That gives us c is the capacity of E. That's how capacity was defined. It is E to the negative VE. So this is great. We've now got another way to find the capacity if we have a conformal map. So any set where the exterior is simply connected, if we can construct that conformal map, we can find capacity. Another way of writing this would be C is 1 over phi prime of infinity. It's a good thing we said earlier that the phi prime has to be greater than 0, so C is a positive number and defined. That was in the way we had the theorem we showed earlier. The unique Green's function has to have C, has to have that derivative positive. Let's do an example of how this can be useful. So let's take the standard, the most common set we might work on, and that is the, it's not writing right, the interval from -1 to 1. So these are real numbers, and we want to find the capacity from this. And there is another way that I tried to figure out using the arcsine function, and it did not make a lot of sense to me, so I'm happy to have this other way to do it. So let's take this map. Phi of z is 1/2 z plus z inverse. This is called the Joukowski map, and it's what it does is phi maps the boundary of the disk to -1, 1 as a 2-to-1 function. So we have the disk here. And it's going to map the boundary onto this interval. The 2-to-1 is because we take a z here and a z inverse here. Each of them is paired with the other one, so if you pick either one, we'll get the same result. If we add them together, we get a real number, and then take 1/2. This essentially gives, it projects it down to this point in the middle. So it has two different points that project onto it, meaning it's 2-to-1. What about the rest of it? Well, the inside of the disk maps to everything else. And so does the outside of the disk. So it's 2-to-1 onto everything. I guess the only exception is 1 and -1. This is the only point that goes to 1, and this is the only point that goes to -1. But other than that, every point gets hit twice. So we're going to specify, let's focus on the one that deals with the outer part, because that's what our theorem has to do with. So let me clear this off for a sec. Let's declare psi specifically to map the exterior of that closed disk, everything with greater absolute value, to omega, which is the complex plane not counting -1 to 1. So omega is the exterior of E. Omega is simply connected because there's this one interval in the middle and there's no holes in the exterior of that. Now what do we know about that? Well, phi of infinity will be infinity. We take z to infinity there, the z inverse disappears, so the z dominates and gives infinity. Psi, did I say phi? I meant to say psi. I get my Greek mixed up. Psi prime of z is 1/2 1 plus, I guess, -1 over z squared, which at infinity would give us 1/2. which is greater than 0. So this is the psi that will work out. Problem though, we wanted psi to go from omega to the exterior of the disk, and it doesn't. So we need to invert this function. So let's do a little algebra. We have z equals 1/2 w plus w inverse. And let's solve for w. That becomes, let's multiply on both sides, 2z equals w plus w inverse, or 2z equals w squared plus 1 over w, which would imply 2zw is w squared plus 1, or 0 equals w squared minus 2zw plus 1. Now this is a quadratic equation, so we just use quadratic formula here and say w is z, I'll trust you can work the quadratic formula on, plus or minus z squared minus 1. What do we do with a plus or minus? Well, we said we want to go to the exterior. If it were minus, the z and the z squared would partially cancel each other out, and that would give us a small value. So we use the positive one. So let's just go ahead and delete that negative there. So that's our function. So therefore, we get that the inverse of this, phi of z, is z plus the square root of z squared minus 1. And this again is the property that phi of infinity is infinity, and phi prime of infinity, well, that's greater than 0. I don't want to work out the whole thing explicitly. I think you can reason out that it's greater than 0, and you can work it for yourself if you need to. So that means the Green's function is the log of this. So look at that. We have a closed form for the Green's function. That's nice, because usually the Green's function, the potential involved this whole elaborate integral process. So here we don't need one. What happens when z goes to infinity? Well, then actually all we care about is what the phi, not the log part. The phi of z goes to -1 becomes irrelevant, so we're left with z plus square root of z squared, which would be 2z. So the capacity is 1/2. And that's consistent with the more general formula, which is it's b minus a over 4. In this case, b minus a is 2 over 4 is 1/2. B and a being the endpoints. But we could also rearrange this, and we could say the Green's function we know is VE minus mu. So VE minus, or u to the mu e, equals log of z plus square root of z squared minus 1. And then solve that for u. U, mu e of z, equals v of e minus the Green's function. So that is u to the mu e of z equals log of 2. Capacity is 1/2, so the energy turns out to be the log of 2, minus log of z plus square root of z squared minus 1. So again, we now have a closed form for potential. If we are dealing with just the interval of -1 to 1, we can plug in any point to this formula and get the potential at that point without having to deal with all the tedious process of integrating. Which is great, because potential, having to deal with it, it was really hard to work out exactly what numbers it comes out to at different points. And now we've got a shortcut. And we can deal with this to get rid of one of the big hassles we've been having all along, which is regularity. So, all along we've said we've got this set, and the Green's function is 0 quasi every point on the boundary. But what about those exceptional points? Well, here's a theorem we can have. If omega is simply connected, then it is regular. This kind of feels right to me. If we think about the things we've been dealing with, it's hard to imagine how a function could be 0 here and then not 0 somewhere else. If we had some exceptional point where it's some k, there has to be points nearby where it's 0 because it's a small measure set. It can't have an entire interval to itself. But the limits have to be 0 there. So it's hard to see how you can do that and preserve continuity. And this says you can't. So what kind of points would be irregular? Well, if it's not simply connected. So if we had like a point out here, it might be that the Green's function is positive on that point. The Green's function is 0 on the interior and the boundary, but as it goes away from the boundary, it can become positive. So there might be exceptional points outside the main portion of E that are technically still part of E, but are so isolated from the rest of it that the Green's function is positive and it's irregular. And it's a pretty simple proof once we've laid all the groundwork here. All right, so we know log of absolute value of phi of z. That is our Green's function, and it is continuous when phi of z is non-zero. Since phi maps omega to the exterior of the disk, we know it's not going to be 0 on all of omega. And we know phi of the boundary of omega will be the boundary of d01. So log of absolute value of phi of the boundary of omega is just log of 1 or 0. So notice this is for every point. It mapped this boundary to this boundary. So every point on the boundary ends up valuing to 1. Green's function is 0 on the boundary of omega, which is also sometimes written as the outer boundary of E. So omega is regular. This is not an if and only if statement. It might be there's a regular function even if omega is not simply connected, or a regular set. But so that includes intervals. Intervals are always regular. So this is helpful. This is something that's going to be very useful in our studies, because what we're really looking at is points like this, or sets like this. This is what we started with our Chebyshev polynomials. And these irregular, isolated points, is that the same thing? We've said right now that this set is not simply connected. That said, each of these intervals is, so the Green's function on this interval by itself would have to be 0. On this function, this interval would have to be 0. So it seems plausible that the Green's function for the set entirely would have to be 0 on the intervals and non-zero on the isolated points. And that really is going to be our window into dealing with Chebyshev polynomials. So I will see you back there.